On va passer maintenant à la deuxième présentation. Our next speaker is Enrique Mateos-Espejel. Dr. Mateos-Espejel is research scientist in the process engineering program of FPInnovations, that is Canada's National Forest Products Research Institute. He received his degrees from Universidad de las Américas Puebla, Polytechnique Montreal, and Concordia University. He is an expert in energy efficient optimization, process integration, and process modeling. He's contributed to the development of holistic methodologies to improve the energy efficiency of pulp and paper processes while considering energy, water, and technical economic aspects. In fact, he received the PAPTAC 2011 I.H. Walden Award for his work on energy sustainability of the Green Integrated Forest Biorefinery. And he will speak to us today about how to successfully apply energy efficiency techniques in the pulp and paper industry.
Good evening to everyone. Thank you very much for coming to this presentation. So, as you can see in the title, the subject is going to be kind of similar of what just Professor Paris talked, but it's going to be with a much lower level of detail. So I hope if there's something that you didn't understand in the previous presentation, I hope you will understand in this one. So what I want to talk about today is I will just give you a brief explanation of what FPInnovations does and what we are. Give you what's the context of the pulp and paper industry, what's an integrated forest biorefinery, what is process integration and how can we benefit from it, the success factors for the optimal implementation of energy efficiency techniques in the actual processes, some examples and the conclusions. So what we are, FPInnovations is a non-for-profit organization. So we are a unique forest R&D center that considers the full value chain of the forest. So we have members, approximately 210 throughout Canada. So that means Canadian mills, governments, universities. And we have world-class R&D facilities. We have pilot machines. We have many R&D projects. We are very active in developing patents. And as you can see here, like we have been around for a while. FPInnovations is the merger of three former research institutes. The first was the Pulp and Paper Research Institute of Canada, then the Forest Engineering Research Institute of Canada, and the Forest Products Laboratories. So in 2007, the three organizations merged to have one voice when dealing with the forest industry. So that's how FPInnovations was born. We have 10 research programs. So basically, when we talk about energy, we talk in the biorefinery and energy sector, but also when we talk about market pulp. So this is when we talk about energy efficiency that are related with projects. But when we talk about PIT, that is our, well, it's one of our programs. They look at energy efficiency since the perspective of cars and improving the efficiency of fuel combustion and stuff like that. So you can see that we see energy efficiency from many perspectives. But me, myself, I work in the market pulp and the biorefinery program. So just as Mr. Paris just mentioned, like the pulp and paper industry was a big contributor to the Canadian economy. It still is a big contributor to the Canadian economy. However, during the economic downturn of the industry and also the global economic situation, that had a negative impact on the Canadian economy. So the industry start thinking themselves that what they can do to improve and become more profitable and still remain part of or a big contributor to the Canadian economy. So they try to look first as cost reduction. For example, here's where energy efficiency techniques appear, but also as a way, they wanted ways to diversify the products that they were producing. So for example, the ideas that appear is like they should enter in the textiles, produce fuels, polymers, chemicals. So there is a bunch of options that appear and that need to be still evaluated. The the forestry has an advantage, for example, when we compare ourselves with agricultural land, because we don't use agricultural land, so that's when we're not competing for producing food for human beings. The area required is lower, it's a lower carbon footprint when we compare to that, and also we don't use pesticides or fertilizers. So when we talk about biorefinery, this is the typical definition, that is the utilization of forestry biomass to produce a spectrum of products by various extraction and transformation pathways. However, as you can see, Professor Paris already explained, like the raw material to any pulp and paper process is wood chips. So wood chips has three main components, that is hemicellulose, lignin, and cellulose. So when we produce paper, basically we want the cellulose out of it, mostly out of it, a little bit of cellulose. And as you can see, pulp and paper mills are already biorefineries because these two compounds, they use them as fuels to produce energy for the same process. So in industry, the processes are already a kind of biorefinery, but however, now what we are looking for is to use these two and to produce value-added compounds that will bring more revenues to the industry. So then we will remain economically profitable. So to give you a context in terms of the energy aspect of the industry, the pulp and paper Canada is Canada's most energy-intensive sector, well, in the manufacturing industry. It accounts for 25% of the total manufacturing consumption, 30% of the total manufacturing cost. And one important thing is that all the energy that the process or the pulp and paper industry use, 55% of that energy is generated from biomass. So still, there is a 45% that comes from somewhere else. Fossil fuels, or it comes from electricity generated by different means. So that means that the industry needs to look for energy efficiency technologies. There's where this comes in place. Also, water conservation alternatives. And as Professor Paris explained, in pulp and paper processes, water is used, but this has a big relationship with the utilization of energy. If a process uses too much energy, too much water, that means that the process is using too much energy. So that's why we need to take a look at both aspects when we evaluate or we try to improve the energy efficiency of a process. So what we want is a systematic energy optimization way to improve the energy efficiency of pulp and paper processes in a cost-effective way. That's very important. So to give you an idea, as Professor Paris mentioned, there has been a decline in the pulp demand overall. So that means that the current processes of the current pulp and paper mills, they were designed to another capacities. So now the mills are working with a different set of operating conditions, with a different configuration, and with different utility systems. Those are the systems that deliver the steam and the hot water and the process require. So that means that the initial design of the plant is completely different to how it is operated. So that means that there is a need to improve the operations of the process. And more than a need, it's also an opportunity for the mills to reduce their cost, energy cost, and also to diversify the revenues that they generate. So for example, when we look at energy efficiency in a mill, we try to optimize the capacity that they have in their boilers, in their turbines. We try to improve the current heat recovery measures that they have in place, and also identify new ones if it's possible. And also the thing that we also look is diversify the revenues. So here I just wanted to put an image of what a pulp and paper mill looks like. So you can see there is a lot of steam going on. So this is a lot of energy that is being wasted. So you can see that there is still, even though pulp and paper mills are integrated, there is still a big opportunity to recover the energy and to make them more profitable. So just to give you a brief explanation of what's a pulp and paper mill. This is a craft process. So basically, you have a chemical lignification part where you separate hemicellulose, lignin, and cellulose. So as I said before, what we want for the final products in the paper is mainly cellulose. So in the washing and the bleaching sections, we take out all the lignin and hemicellulose that remains in the process. Then we dry the cellulose, and that's what our final product. In the recovery cycle, what we do is we recover all that lignin and hemicellulose that remains, and we just burn it to produce a steam that is then used in the process, and also to recover the chemicals that were used initially. So you can see that the process is already kind of integrated, and that's what makes it economically feasible. So just to go a little bit more in detail, so you have, as Professor Paris mentioned, the pulp line, and you have the recovery loop. But all around this process is where all the energy is produced. So we have an steam system that delivers we produce steam through different types of boiler that can be used in biomass, can be used as fossil fuel. Some of them use the black liquor, that is the hemicellulose and lignin that that is contained in the wood chips. And we are using water. So part of the steam, nowadays, pulp and paper mills are looking, one of the ways of diversifying their revenue is to produce power. So the mills is the user of the steam, so units such as condensing turbines or back pressure turbines can be used or has been implemented in pulp and paper mills to export power to the grid. So, and then, in addition to the complexity that the process already have, if we want a biorefinery, then we will add complete new processes. And the way it is, or one of the advantages that integrated forest biorefinery has, is that it has the kraft mill with already all the utilities, already all the heat and water. And we just need to find a way to integrate them, so to make them, again, more profitable. And there are other options, like, for example, using a good gasifier. So they can produce additional compounds, additional value-added products, power, and then supply the steam that the whole biorefinery will need. However, we need to maintain the core product so the mills can still run. So there are some advantages of the integrated biorefinery over a new biorefinery. So, for example, in kraft mills, there is already the infrastructure in place. So that means we have all the support networks, all the direct access to the raw materials. There is attractive utility cost, and there is qualified manpower to run the mills and to run the new plants. So there is everything already in place, and there is a full of infrastructure that can be used to integrate the process. We don't have to start from zero. So, however, there are challenges. So energy efficiency must be improved, because there's going to be a reduction of what we were previously using as a fuel for the process. So now we want to use lignin and hemicellulose for another value product. So that means that the process has to be more efficient, so it doesn't increase its energy consumption. And also, we don't want to increase the water consumption and effluent production. So one thing that characterize the way that we approach the studies, or what we do, process integration. When we talk about process integration, we analyze a process as a whole. So we don't optimize just specific parts. As I just mentioned, the pulp and paper mills have different departments. Every different department has a different need for steam, a different need for power. And so when we look at the process, we look at the process as a whole. So that's because what we found, or what was found before, is that when you're looking just specifically and optimizing one part of the process, that might have a negative impact somewhere else, and the overall efficiency of the process will not be improved. So that's the main mindset that we follow when we do, or we'll target energy efficiency. So process integration is a site-wide approach that identifies and corrects the inefficiencies in complex industrial processes, such as a pulp and paper mill. So as mentioned before, it's a global analysis, and what we want is to determine where the heat is used, where it should be recovered, and how is the best way of doing it. So this technique, process integration, it's a best available technique, and it has been used in the pulp and paper industry and gets savings between 10 and 30% reduction of the energy consumption. So you can see how powerful it is if it's correctly applied. So again, I come back again to the same diagram that I mentioned before, but much more simplified. So you can see the energy flows that exist within a process. So what we want is basically we want to maximize all the energy that is used within the process while we are minimizing the fuels and minimizing what we are wasting. Because the energy that, if the process is not efficient, every extra of energy that we put is extra energy that is degraded and then sent to the sewer or sent to the environment. So you can see how powerful is the technique that we use. So the technique that we use, as Professor Paris mentioned before, I maybe just going a step backwards, it's based on a graphic representation. So what we look is at the quality of the energy that is used in the process and the quantity of the energy that we are using. So basically, when we have a chemical process or a pulp and paper processes, what we supply to the process is a high temperature energy source. In this case would be steam. Let's say normally we supply steam at 140 degrees Celsius. However, the process requires at a lower temperature, a lower quality on energy, around 70 degrees, most of it, let's say, to heat up water. And then there is energy that is going through the effluents. So normally this energy goes at, let's say, between 50, 30 degrees Celsius. So that means that what we are, again, looking is to reuse the energy that we are using at this stage, so we don't waste high temperature energy that could be used for something else. So here is where the pinch diagram comes in. So this is, again, is a representation of the temperature, that is the energy quality, and the enthalpy, that is the energy quantity that have a process. What is very powerful of this tool is that it's a representation of the whole process. So we have all the streams that need to be cooled down, and we have all the streams that need to be heated up. And what it gives us is just a target. So it will give us how much, the minimum theoretical heating requirement of the process, and the minimum theoretical cooling requirement of the process, or the minimum energy that we will be wasting. Okay, so this is just a parameter that we use to identify the projects that we are going to implement in mills. There is another tool of the analysis that is also based on the temperature versus enthalpy diagram. It's called gram composite curves, and it's just a profile of the process, temperature profile of the process. And what it allows us is to determine what's the temperature of the utility of the steam that needs to be used. So that will help us to increase how much power we can produce. And if we are to implement heat pumps, it also tells us where the heat pump should be placed, so we actually recover energy. So just since a practical perspective, so in order for this to be successful, yeah, it seems very nice, and yeah, it's a great methodology, and I can tell you theoretically it works perfectly. But when the thing is that in the situation, in the context that we were working, it's mills that are already there, mills that already have internal heat recovery measures in place. They already have a mindset about energy. So when we go there, so the first thing we need to do is we rely a lot on how we communicate with the engineers there. Normally, when we come with the people that works in the process, they know the limitations, they know the constraints of the process. So really, we need that and include that in our analysis. If not, anything we propose is not going to work. So that is the key part. Then we also use a computer simulation. Well, that obviously has helped us to try scenarios of what will be the impacts of changing the operating conditions of the process, or introducing new measures for internal heat recovery. We also, the quality of the information that we receive. If we don't have if we don't know properly, if we don't have a good set of data to do the evaluation, anything we propose is not worth it. It's like garbage in, garbage out. So just to give you a brief, this is an example of a current mill. Okay, so as you can see, it's very, very, very difficult. This is just a water network. Okay, so what we were looking here is these are different departments. It's not actually the same department. So what we were looking, since a process integration perspective, is to reduce the overall consumption. So we realized that the mill was using fresh water, and then they were using steam, and then they were sewering to the effluent. So it was as strict, and then they were using fresh water somewhere else. So imagine that you're here in Canada, you're in the winter, you're heating water at 60 degrees, and there you're using somewhere along the process, not maybe in the same place, water at 2 or 4 degrees. So that's very inefficient. So maybe one person in one department will not realize, but when we look at the whole picture, we identify that that's something that needs to be improved. So maybe the saving will not be, the saving for sure will not happen here, but will happen here. So that's a mindset that we'll bring. So for example, just to give you an idea of this, what we found in this case. So when we realized that the mill has this problem, so there was no need to invest in capital, and they were able to reduce water, they were able to reduce their steam consumption, and they have benefits. Like for example, the savings that they get were $200,000 per year, and it could increase to $500,000 if they consider something else. So you can see of what the impact of these projects can have. It's immediate. So other aspect that I mentioned before is the optimal integration of the biorefinery technologies. So for example, we look at lignin extraction. So in FPInnovations, we already have, we have the patent a way of extracting the lignin that it's been already been implemented in one mill in Alberta. So, but when we look at a process integration perspective or energy efficiency perspective, we have to look at the chemical, how extracting this amylosis lignin will impact the chemical balance, how it will impact the effluent treatment, and then what will be the overall impact in the energy balance. So when we apply, or once we are about to implement a biorefinery technology, it's good to look, since a process integrations perspective, since an energy efficiency perspective, what will be the impacts on the overall mill. So for example, here you can see I put an example of the lignin that they are producing. So another example, it's for example, if we want to convert a kraft mill to a dissolving pulp mill. It's just a different type of product. In pulp, you have cellulose and a small amount of hemicellulose. In dissolving pulp, you don't want hemicellulose at all. So the one objective would be to convert the mill and extract the hemicellulose so we can produce something else. So here, the only thing that I wanted to mention is that, and what we evaluated when we were doing that, is that when we were extracting the hemicellulose and how it was done, that was changing the overall balance of the mill. So that was giving, so that was changing the requirements of the mill, and also it was changing how an internal heat recovery measure need to be implemented. So for example, if the mill was thinking and implementing something before the change, they actually should wait till after because the whole overall balance will change. So just to give you an idea, so this was a product that they had initially, and this was the product that they were going. They were trying to target something in the textile. That was a raw material to produce in the textile industry. So another example is now, for example, I mentioned before that you are going to extract the hemicellulose. So then what do you do with the hemicellulose, for example, in this case? So for example, we evaluated, actually it's something that I did when I was in the university, is we evaluate the impacts of a biorefinery that produces ethanol, okay? And then how will that interact with the mill? So you can see, like, normally what we found is that the opportunity of heat recovery was coming actually from the biorefinery or from the ethanol producing facility to the mill. So that was the way the energy was going to be. So for example, this is just a representation of the energy balance, of the temperature that was required, this process was rejecting, and where it could be used in the process. So that gives us an idea of how the two processes could interact and how that will reduce the overall energy consumption. So one of my last points is something that also makes this type of project worth it to the mills is that these studies, this process integration study and looking at the overall steam and energy balance of the process are very intensive. So that means that we have a strong collaboration with the process, with the mills. So at the same time that we are doing the study, the mill is taking also a closer look at how they are operating. I had an experience where we were doing a full study in the mill, and as we were doing the study, the mill was realizing that the way they were operating the boilers was not optimal, and they were actually, before even finishing the study that we were doing, they were getting savings that was worth how much they were paying for it. So they get this benefit that they get develop an energy culture, and also they start thinking also in a process integration perspective when they look at energy efficiency. So they not only look at one process, but they start also looking at what they are doing in their part of the process that will have an impact somewhere else. Because sometimes what happens normally in the mills, or some mills, is that they are just concerned with the operation of their department, they are not concerned with the operation somewhere else. And that has an impact when we look at the big pictures, and that's the perspective that process integration brings. So to finish, pulp and paper mills can recover millions of dollars through implementation of energy efficiency measures. And energy optimization is required for a sustainable forest biorefinery. What we found is that to be successful in applying this in the real process, apart from the methodology, apart from the understanding of what process integration is, we need a close collaboration with the people involved. We need an expertise and understanding of how the process, how it is operated, why the operation conditions they have are like that. And well, that we also develop an energy culture in them. So what I mentioned before that thermal energy savings are possible between 10 and 30%, and they can reduce their fuel, they can increase power regeneration with that, they can improve their water conservation, they can debottleneck the process that can even help them to increase their production in some cases, and of course they will get financial gains and improve the profitability of a future forest biorefinery if that's the case. So thank you very much, and I hope you enjoyed this presentation.